this refers to certain specific arrangement. If you look up this different types of machines, you'll find different configurations, and you can select what you want. And then there's another one, the duty here. That's so duty S1 means there are different classes of duty. So S1, 2, 3, 4, 5, 6. So the first one is like continuous duty. You can operate it continuously forever. It doesn't matter. It's rated for continuous duty operation. So S2 means it's like you are not allowed to operate it continuously. You've selected this machine to work. Let's say it will work for 5 minutes, and then you have to leave it turned off for half an hour, and then turn it on another 5 minutes, and then half an hour turned off. So that's called intermittent duty. And then S3 might be like short time duty. You just work it really hard for a really short time, and then you work it half the rated power for a longer period, and then again full power. So there are different types of duty operations. So we'll be covering those stuff in variable speed drives in fourth year, I think. So that's like drives related stuff. So that those are some of the specifications you'll find on the data sheet of the nameplate of the motor. So in this case, so S1, it's a continuous duty motor. So from this information, we can do certain calculations. So this is the nameplate of the DC motor, the rated shaft power and the rated armature voltage and current and the rated field voltage current information are given. The rotational losses at rated speed is found to be 310 watt. So that's not given. So that depends on how well the rotational losses might change with time as well. So to determine that, you have to do certain tests like no load power consumption. That will give you like the sum of copper losses as well as rotational losses. So that has to be determined. It's not part of the data sheet or the nameplate rating. So part A is calculating operating point conditions, rated conditions. So part A, it says calculate the rated mechanical torque. So you are given the rated power output, that's 12.5, and you are given the speed as well. So then you should be able to figure out the rated torque. So for part A, you are given, we have the rated power, that's 12.5. So the rated torque will be rated power divided by rated speed. So this is the 12,500, that's 12.5 kilowatt divided by 1,500 RPM. So this is revolutions per minute. So we have to convert it to radians per second. So that will be 2 pi over 60 gives you the rated torque. Which is 79.57 Newton meter. So you are given the total armature current. So if you look at the equivalent circuit, you'll have something like this. So this is the armature circuit, and then this is producing 12.5 kilowatt, and then you're feeding this in with a certain voltage, which the nameplate says that's 495 volts, and the armature current is given as 29.9 amperes. That's the armature current and voltage. So the second part, it says calculate the armature and field winding copper losses at rated conditions and hence the total copper losses. So we have the output power from here, that's 12.5, and then from this information we can find how much power you need to put into the armature. So P in so the armature input power will be the armature voltage times the current into the armature, which is 495 times 29.9 gives you this gives you 14,800.5 watt. That's the input power to the armature. So the power difference between the output power and the input power corresponds to this the power losses in this particular resistance, the armature resistance. So P, let's say copper loss in the armature will be the difference between these two. So 14,800.5 minus 12,500 gives you the armature copper losses, which is 2,300.5 watt. That's the armature copper losses. So in addition to this, you also have the field circuit. So this is the field circuit, and it's separately supplied by a voltage of 300 volts and a current of 2.18 amperes. So there's a power loss in this field circuit as well. So that power is just the voltage, field voltage times field current. So the copper loss in the field winding, P copper loss in the field winding will be the field voltage times field current, or if you know the resistance in the field circuit, you could do I squared R as well, so it's the same. So this will be 300 times 2.18. So you have 654 watt power loss in the armature. Oh, sorry, yes, field winding. So we forgot one loss which is mentioned. So 310 watt, it says 310 watt is due to the rotational losses. So you have some rotational losses here as well, P rotational losses. So that means the difference between these two values includes the armature copper loss in addition to rotational losses as well. So this includes rotational losses as well. So armature copper losses plus the rotational losses is the difference between the input power and the output power. So you are putting in 14,800.5, you are getting out 12,500. So the loss is due to the rotational friction and windage losses and the I squared R in this here. So that's these two, the sum of these two. So this is given to us as 310 watt. So then the copper losses will be this minus 310. So P copper losses in the armature will be this minus the 310. So that's 2,300.5 minus 310. You 0.5 watt. So these are this is the armature copper losses, field winding copper losses, and the rotational losses. So those are the loss components in the machine. So the total copper losses will be the sum of these two. So P total copper losses will be this plus this, which is 2644.5 watt. That's the total copper losses. So that's for part 2, second part of that. So third part of that question is estimate the armature resistance. So we need to find the resistance here, RA. So we know the power loss in this element here, and we know the current through the element, so we can estimate that as I squared R. So P armature copper losses will be I squared R, IA squared RA. IA is given as 29.9, so this is 29.9, and this is equal to 1990.5 watt. Do you want this as well? Going through this one. Yep. So we have this, and then if we can find RA by 1990.5 divided by 29.9 squared. Which is 2.23. And the fourth part is to figure out the field winding resistance. So you are given the field winding voltage and current. So that's purely resistive. So voltage divided by current will give you the field winding resistance. Fourth part, so VF will be just RF, IF. So we know VF and IF, so we can estimate RF as VF over IF, which is 300 divided by 2.18, which is 137.6 ohm field winding resistance. So fifth part is to find the back EMF under this operating condition. So you are given the voltage here, and we found out this resistance as 2.223. So one approach is to apply Kirchhoff's voltage law. This you have a certain voltage drop across this resistance. So that this voltage minus this gives you the back EMF here. You can calculate the back EMF that way, or you can say that back EMF times current, that's the power, electromechanical power output, and then you can estimate that way as well. You should get the same answer either approach. So if you do the first way, we can write the terminal voltage VA equals EB plus IARA. This is for a motor where the current is going into the circuit here. So then the voltage drop across the armature resistance will be the resistance times current. So here it's 495 volts, and this is going to be 2.23 times 29.9. So EB will be so this is going to be 66.67. So 495 minus that gives you 428.32 volts back EMF. This minus this value. So the alternative approach is to consider the electromechanical power developed by this. So PEM here will be, so for this PEM will be the output power plus the rotational losses. So you have 12.5 kilowatt output power and then 310 watt rotational losses. So PEM will be 12.5 plus 3.31, which is 12.81 kilowatt. That's the PEM. You can also write this as EB times IA. So then EB will be PEM divided by IA. So which is 12 point, I'll write it as watt, so that's the PEM divided by 29.9. So you should get a similar answer here as well. So 428.4 we get volts. So either approach is valid. It's the same calculation in the end.
Sorry, how did you get PEM? You did the EB by
PEM is equal to EBIA, so PM divided by this. So either way, it's okay. And then sixth is to estimate the efficiency of the machine. So you have the output power, which is 12.5. You have the armature input power. So the efficiency will be the output power divided by total input power, which includes the armature input power plus the field winding input power as well. So P in armature plus P in the field winding. This is the total power input. So this is 12.5 and this is 14.8, and then field winding power is the field winding voltage times current, which we found as 0.654 kilowatt. So everything's in kilowatt. As a percentage, we will have 12.5 divided by which is 15.454. Which is 80.88% efficiency. So that's part A, based on, everything's based on the rated operating condition. So this all corresponds to the values given in the nameplate, the rated condition values. So second, part B of this is not the rated operating condition, different speed at different load conditions. So it's a completely different operating point. Any questions on this, the first part A?
So we're assuming that it's running slower because the load is greater?
For the part B, is it?
Yeah,
No, it can be different terminal voltage. The terminal voltage might be reduced.
Right, so it's going to be
Yeah.
less than 495?
Yes, yeah, yeah. So part B, so this says the motor is operating at a condition where the speed is 900 RPM and the rated armature current is 20 amperes. The field winding is applied at its rated voltage of 300 volts. So the field circuit is kept at the rated condition. So the field current is the same. There's no changes in the field circuit. So now the circuit will be, you'll have some voltage here, VA, and then this is rotating at a certain speed, it's a 900 RPM, and the resistance, armature resistance doesn't change, so that's the value we calculated before, 2.23 ohm, and this is conducting a current of 20 amperes, so that's the operating point. First part of that is to calculate the new back EMF at this speed. So as we recall from the lectures, you did the back EMF is equal to some factor IF times speed. So this is the back EMF relationship with field current and speed. So in this part, the field circuit doesn't change. So this is constant. IF remains the same as well. So compared with part A, the back EMF changes with speed. So previously we had EB of 428.32. This was at a speed of 1500 RPM. So if the speed drops to 900 RPM, the back EMF will drop linearly as well. So the new EB, let's say new, will be 428.3 times 900 over 1500. This is the new back EMF. Which is 256.98 volts. So that's for part A. So this is now at 256.98 volts. Second part, calculate the terminal voltage at this operating condition. So you have the current, you have the back EMF, then you can find this voltage drop across this armature resistance. So then for part B, the terminal voltage will be EB plus IARA. So that's 256.98 plus the voltage drop across this, which is 20 times 2.23, which is 301.58 volts. That's the voltage that you need to feed to work the motor at that particular operating point. And the third part is estimate the rotational losses at this speed, assuming the rotational losses scale linearly with speed. So see, the rotational losses, as you probably came across that in the lectures as well, the rotational losses is purely a function of speed. So if speed changes, the rotational losses change. But if the load changes, mind the rotational losses don't change. If it's at the same speed, different load, the rotational losses remain the same. So P rotational losses is proportional to speed. We assume this relationship because that's given here. So at 1500 RPM, we have 310 watt rotational losses. We need to find the rotational losses at 900 RPM. So P rotational losses new will be 310 times 900 over 1500, which is 186 watt. That's the rotational losses we've estimated. And then fourth part, calculate the output shaft power and torque produced by the motor at this operating point. So we have the rotational losses. So P out, that's the output power, is the electromechanical power developed by the motor, PEM, minus the rotational losses, new rotational losses. So we know this value, that's this one we estimated. So we had to figure out the electromechanical power developed by the motor. PEM is the power consumed by this element, which is the voltage across the element times the current into that element. So that's the EB times IA, which is 256.98 times 20. That gives you the power, electromechanical power, which is 5139.6 watt. So the output rotational power will be this minus the, output useful power is this minus this, which is 4953.6 watt. And then you have to find torque as well. So the output torque will be the output power divided by the shaft speed, which is 4 4953.6 watt divided by speed. It's rotating at 900 RPM. So then that's 900 times 2 pi over 60. This is in radians per second. Sorry, radians per second. So that's 52.56 Newton meter torque. And then on that part, finally, you have to estimate the efficiency of the machine. So you have the output power, that's this value. That's the output power. Input power is the terminal voltage times the current armature input power. CDE, sorry, this is part, the fifth part, right? So P in to the armature is the armature terminal voltage times armature current. So that's 301.58 times 20. Gives you 6031.6 watt. That's the armature input power. And the field winding input power is the same as before. We didn't change the field winding, which we calculated before as 654 watt. So the efficiency will be the output power, which is 4953.6 divided by the total input power, that's this plus this here, 6031.6 plus 654. Any questions on that part? So part C of that is related to DC motor starting operation. So I think you've gone through starter operation of the DC motor starters in some of the lectures, I think, isn't it? So DC motors require a special form of starting methods. So modern DC motors, I mean, you'll have some kind of voltage regulated supply here, which you can have low voltage when it's starting and then ramp up the voltage. But then if it's like high, if there's no point in having a voltage regulated supply here, then the crude method is to have series resistances. So in this case, the part C, first part is to calculate the armature current if the motor is energized with the 495 volt at starting. So part C, so we have the same circuit. So we are applying 495 volts and this is 2.23 ohm, and at starting the speed is 0. So the back EMF here is 0. So effectively you have this 2.23 being short circuited over the full voltage. So the starting current under this case would be just that voltage divided by the resistance. So I start would be 495 divided by 2.23, which is 221.97 amperes. So if you look at, compare it with the rated current is just 29.9. But if you were to apply the full voltage at 0 speed, you have almost like nearly 7 or 8 times more than the rated value. So which might burn out the motor, or it might damage the supply, which it's the power is being supplied, or it might trip. So one approach is to have series resistances. So this is for part A, and part B. Now you are connecting an external resistance. So this is the external resistance, and you are applying the full voltage with that combination. So this is the external resistance, and this is 2.23, and this it's starting, so it's 0 volts here. This is 495. So we want to limit this current at the rated value, which is 29.9. So this current, we need to limit it at 29.9. So we can write the Kirchhoff's voltage law to this. R external plus 2.23 times the rated current should equal the full voltage we have, and that's the Ohm's law. So the total resistance has to be 495 divided by 29.9, which is 16.55 ohm. That's the resistance we want. And the external resistance will be 14.325 ohm. So once you apply this voltage across this, you'll have rated current, and then you'll have the rated torque being produced. So it will start up, and then at some speed, the voltage drop across these two will be large, and then this won't be able to speed up to the speed you want. So at some point, you need to disconnect this, and then if you were to disconnect this and apply full voltage, still you'll have a huge voltage drop across the resistance, and the current will probably exceed the rated value. So one of the starting methods is to have like a cascaded arrangement of resistors, so that when the speed increases, it steps through the resistors. So that's like instead of one resistor, you have like series of resistors. So this is the equivalent circuit, and then you have the full voltage, let's say 495 volts, and then this steps from high resistance to low resistance, and then gradually to short circuit it's off at near the full speed. So this is, let's say, at 0 speed, and then it grows up to full speed here. So it can, depending on speed, this will step through resistances. So you'll have a high resistance here. Let's say I'll call that R1, R2, R3, and then it short circuits. So in the part C of that, or the third part of that question, says a 4-step starting resistor changed at 0 RPM, 500 RPM, 1000 RPM, and 1500 RPM is to be used to limit the armature current to its rated value during startup. Calculate the required value of the resistors for this starter circuit. So we want at 0 speed you have this high resistance, and then you switch onto this particular resistance when it's at 500 RPM, and this is sized such that the current is at rated value, and then at 1000 RPM you switch onto this particular resistance, and then when it's at 1500 RPM it switches onto this other resistance. So we already calculated R1, which is this value here. That's the resistance we want when it's starting. So that's 14.325. We need to calculate these two resistances. So at 500 RPM and 1000 RPM. So then if you look at the circuit, so you have some back EMF here, EB. Let's say if we consider the 500 RPM case, we can write the terminal voltage VA is equal to R2 plus the armature resistance times the rated current plus EB. This is at 500 RPM. And this value is at rated conditions, which is 29.9, and this is at 495 volts. This is 2.23. We need to find the back EMF at 500 RPM. So in the previous question, we found the back EMF. So at 1500 RPM, we have a back EMF of 428.32. That's from the previous section. So EB at 1500, we found that as 428.32 volts. That's the back EMF at 1500. So EB at 500 will be 1/3 of this. So that's like 500 over 1500, 428.32. Which is 142.77 volts. And then at 1000 RPM, the back EMF will be 2/3 of this. So that's 1000 times 1500 times 428.32. That will be twice this, which is 285.5 volts. So if we substitute that here, you'll be able to figure out the R2 and 3 values. So for the 500 RPM case, we can write R2 plus 2.23 is equal to 495 minus this voltage, which is 142.77, divided by the rated voltage, 29.9. So this turns out to be 11.78 ohm, and R2 will be this minus 2.23 gives you 9.55 5 ohm. So that's the resistance you need at 500 RPM to limit the current to rated current condition. And then if you do the same for 1000 RPM, we can write R3 plus 2.23 equals 495 minus this particular voltage. So that's 285.55 divided by 29.9, which is equal to 7.005, and then R3 will be that minus 2.23, so 4.775 ohm. That's R3. So these are the 4 resistances. One is 14.325, the other one is 9.55, 4.77, and then 0 short circuits.
If you're doing that on a high-powered motor, so it's wasting a lot of power.
It's just the starting transient, so it might be like a couple of seconds. I mean, it prevents it from burning out the or tripping the supply or damaging the supply, so it's kind of a protection.
So it's not really worth getting voltage regulated
Just to start, not really, unless you want speed control, like different speeds. If it's like running, let's say, you have these kind of machines in mining, like the conveyor belts which like transport coal from the mining to the ground. So they run it like constant speed, still like large in DC machines. No voltage regulators there, fixed voltage. Yeah.
The last one, the R4, that would be short circuited before speed. The EB at 1500 is 428 volts. If you were to do the calculation, it wouldn't be actually zero. Is that right?
Sorry again?
So for the resistance necessary at 1500 RPM, if you were to go do the next calculation,
Oh yeah, I mean,
it wouldn't be exactly zero.
yeah, you have one here as well. That's this is the RA as well. So then it will have that armature resistance at that point. Yeah.
Okay.
Yeah. Any questions? So next part is field weakening. So part D. So field weakening, I think you covered that a little bit in the lectures as well. The back EMF is proportional to some factor, the field current and speed. So if you look at the equivalent circuit, so you are applying certain voltage here. So if you are working like variable speed operation, and then you want to run this motor above the rated speed, let's say if you want to exceed 1500 RPM, then your supply here might be limited at a specific upper voltage limit. So in this case, let's say this is fixed at 495 volts, for example. If that's limited at that value, then you can't apply, have enough voltage, you can't increase it above that value to supply the required current to increase the speed above that 1500 RPM. So under that condition, we go into another mode called field weakening. So usually in normal operation, the IF is fixed. So the IF is fixed up to, let's say, speed smaller than 1500 RPM. But then if you want to run the motor above that speed, you don't have enough voltage here. So then we drop this voltage by reducing this IF. So you gradually decrease IF, reduce, which is omega R is above 1500 RPM. So then you have a smaller voltage here, and then with this available voltage, you can supply the required current to produce the torque at that particular speed. So this mode is called field weakening. So if we look at the, let's say, voltage and speed, so let's say this is the terminal voltage and speed. So you are applying a certain voltage, and then at zero speed, you need very little voltage to supply the rated current. So it will be somewhere here, and then you gradually increase with speed, and then at 1500 RPM, you hit that limit 495. This is at 1500 RPM. So then you don't have enough voltage after that. The voltage is fixed. After this particular speed, the voltage remains fixed. But then the field current, IF, would be fixed up to this point. So the field current is fixed up to 1500 RPM. This is normal operating region, and then after this point, you gradually decrease the IF so such that you can achieve that you can achieve that required current at this particular voltage. So then your IA will be around here you'll be producing, let's say, at rated current. So if you look at the torque equation, torque is equal to K times IF IA. So around here, you can supply maximum field current as well as maximum armature current as well. So then you can supply the rated torque up to this point. This is the value we calculated before, which was, let's say I'll write it as T rated, the rated torque. And then after this particular rated speed, you can't produce the rated torque. You can't achieve the rated condition, so you gradually decrease the torque. So if you multiply this by speed, you'll get power. So power output, let's say P will be, you go up to rated condition, so this will be your P rated. And then with speed, you can roughly keep the power constant. It might, depending on how much losses you have, this might not be constant. So ideally, it will be a straight line. This is the power. So armature voltage, field current, torque, and power for normal operation, and above the rated condition, that's field weakening. So part D, first question is to calculate, let's say if you were not applying field weakening, if the field circuit is fed at the rated conditions, then you need to calculate how much voltage you'll need to run it to that speed under no load conditions. So part 1, part D1, so now you are not weakened the field in part 1. The field is applied at its rated condition, and then this is producing 0 watt, that's no load, but then there's some rotational losses, P rotational losses. This is at 2500 RPM. So now this is running at 2500 RPM. So assuming that the rotational losses scale linearly with speed, we need to find what voltage we need to have here. So from the previous section, we have rotational losses, which is, so P rotational losses at 2500 will be 2500 divided by 1500 times 310. So we have 310 watt at 1500 RPM. We need to find how much it will be at 2500 RPM. So we have 516.66 watt rotational losses. So this is 2.23 ohm. So this back EMF. So field current is not changed in this part. So the new EB at 2500 will be, again, you can scale it linearly with speed. So at 1500 RPM, we found the back EMF to be 428.4. Which is 714 volts. So you need 714 volts plus a certain voltage drop here to drive this to that speed. So the current to achieve this PEM, so PEM is going to be P rotational losses so this is 0, and this will be 516.66. So then we can find PEM equals EB IA. We found EB, so we can estimate the armature current. That's PEM divided by EB. Which is 0.7236 amperes. So that's the no load current. So that multiplied by 2.23 gives you the voltage drop. So the required armature voltage to drive this without field weakening will be EB plus IARA, which is going to be 714 plus 2.23 times 0.7236. 715.6 volts. So this is the voltage you want, but then second part it says that how to achieve field weakening operation. So second part, the power source that feeds the armature circuit is limited to 495 volts. Determine the field weakening mode operating condition to achieve a no load speed of 2500. So now this is above that, so we can't run it at this particular condition. So to achieve this with the limited voltage, you need to weaken the field. So then you'll drop this down to a lower value such that the power you want at that particular speed is supplied. So now if we redraw this, so the field circuit is now not the rated conditions, it's reduced field voltage. So this is still, let's say we assume this is running at 2500 RPM, no load, so P out is 0, and P rotational losses, it doesn't change, so it's 2500, it's still this particular value, 516.66 watt. So now you have a new EB value, so this is a weakened field, but you are supplying 495 here, and this is supplying certain amount of current, and this is the resistance 2.23 ohm. So now the current times EB will need to satisfy this electromechanical power output. So here still this is the same as PEM as well. So one equation is, let's say PEM equals EB IA. So we don't know EB, we don't know IA as well. So we have two variables which are unknown. So this is equal to 516.66. Say this is 1. And then if we apply Kirchhoff's voltage law to this loop, we'll have, let's say, VA equals EB plus IARA. So then if we substitute values, you'll have VA is 495 equals EB, which we don't know. RA, we know that 2.23 times IA as well. So these are the two relationships. So we have to figure out EB and IA to satisfy these two equations. So we can multiply this by EB, for example. So let's say 2 times EB will give you EB squared plus 2.23 EBIA plus 495 minus EB equals 0. So it's a quadratic equation. So we multiply all the values by EB. So EB squared, this times IAEB, and this times EB as well. So this term here is 516.6. So we can write this as EB squared minus 495 EB plus 2.23 times 516.66, which is 1152.15 equals 0. So if you solve this quadratic equation, you will find the EB that satisfies this condition. So this is like quadratic equation solution. So it's like ax squared plus bx plus c equals 0. So x is equal to minus b plus or minus 2a. That so then here EB will be minus b, so that's 495 plus or minus 495 squared minus 4a is 1 and c is 1152.15 divided by 2. So this part here, 495 plus or minus which is 490.32 divided by 2. So you have two solutions. So one solution is this plus solution, so that will be 495 plus 490.32 divided by 2. So we have 492.66 volts. That's one solution, and the other solution is the minus sign, 495 minus 490.32 divided by 2, which is 2.34 volts. So which solution do you think is a valid one? This one? We will look at the current as well. So let's say if we substitute this into equation 1, so equation 1 is this, so we can find current. Here IA will be 516.66 divided by 492.66 gives you 1.048 amperes, and then this will be IA will be 516.66 divided by 2.34 gives you 220.79 amperes. So both are theoretically valid operating points. So one is like really low voltage, really high current. The other one is fairly higher voltage, lower current. So which one do you think is the?
You want to increase, well, the back EMF would increase with the faster speed.
Yes, yeah.
Is that right?
No, so the back EMF, so EB is proportional to field current as well as speed. So we are changing the field current as well. So now EB is no longer a function purely on speed. It's which you can change that as well. But we are changing it such that we achieve this much of power, electromechanical power, the voltage remains at 495. So you can run it at that condition. We can change EB to field the excitation field such that the voltage is 2.35, or we can have the field current such that the voltage is 492.66. But if you have this, the current is going to be this. If you have this voltage, the current is going to be this. So this is very high compared with the rated condition. So this one is not the solution 2 is not the practical one.
Back EMF's going in the opposite direction. So the actual supply voltage would be very small.
The supply voltage is fixed at the 400. Yeah.
Yeah, because that's 495 and it's going in that. Back EMF's going in the opposite.
No. It's still rotating the same orientation. So we are just reducing the magnitude of this. So we can have it really small and high current, which will still produce this power. We can have it 492.66 here, and the current is going to be 1.48, and still it will produce this no load power as well.
So you want the 400.
Yes, yeah.
And then, so you could theoretically figure out the field
Yep.
resistance from both of them, but the 400, whatever.
Yeah, so this is the one which has a reasonable number for the current, and yeah.
The rated is 20 amps.
Yes, yeah.
10 times that. What you put in there.
Yep. So this is the rated condition. So the question says the determine the field weakening mode operating condition to achieve the no load speed of this. So then we have to figure out the field current as well. So now we are achieving this much of back EMF. This is the this is the back EMF value. So if you consider the rated conditions, we have a field current of, the field current is given as 2.18 field current, and the back EMF we have is, we calculated that to be 428.4 volts. That's the back EMF. And this is at a speed of 1500 RPM. So if we write the relationship, EB is equal to K times IF omega R. So previously, under normal operation conditions, we keep this fixed. So that's why we can scale the back EMF with speed. But for field weakening, we can't do that. So let's say rated conditions, I'll put 1 here. So that's the rated conditions back EMF, rated conditions field current, and rated conditions speed. So this is 1. And the second new condition, let's say new 2500 RPM condition. I'll put that as EB2, that's K times IF2 omega R2. So that's the new operating point. So now if you divide these two together, you'll have 1 divided by 2. You'll have EB1 over EB2 is equals to IF1 omega R1, IF2 omega R2. So this is the rated back EMF, new back EMF, which we calculated here. The old field current, this is the one we want to find out. And this is the old rated speed, and this is the new rated speed. So we want to find this value here. So IF2 will be IF1 omega R1 omega R2 times EB2 divided by EB1. So this gives you the new field current. So this is 2.3, old field current is 2.18, and the old speed was 1500, and the new speed is 2500. And EB2, that's 492.66. The old back EMF is 428.4. So the new field current is 1.5 or 4 amperes. That's the new field current. So you drop the field current from 2.18 to 1.5, and then that will allow the motor to speed up under no load conditions to 2,500 RPM. Any questions on that? So that's this type of question is fairly complicated. You'll probably not get it in the exam. It's just for your general knowledge. So the test and exam questions are purely based on the tutorial questions. This is more of an extended version. You don't get this like square root calculation in the exam. You'll
Would be on the formula sheet with the quadratic formula.
yes. Yeah. So the third part of that is loaded condition. Since the motor is loaded to 50% of the rated torque at the above speed of 2,500 RPM, and the armature voltage is at rated voltage of 495. Calculate the field weakening operating point and the field winding current for this operating condition. So the calculation is fairly similar to this one, but now it's delivering some load as well. It's no longer no load. So you have this circuit. So it's delivering half the rated torque. So the T out will be half the rated value we calculated. So previously we calculated the first one is 50% of 79.57 half. This is the torque it's producing. So this value is the first answer we got from part A, that's the rated torque. And then it's producing half the rated torque at 2,500 RPM. And this is being fed by 495 volts, and this is 2.23 ohm. And the P rotational losses at 2,500, that remain the same as well as before. It doesn't change with speed, so we can find that from the previous calculation. That's 516.66 watt. So now a PEM is not different to the previous one. So PEM is P out plus P rotational losses at 2,500. P out is the torque times speed. So that's 79.57. This that's the torque times speed is 2,500. 2 pi over 60. So this whole thing within this bracket gives you the output power plus 516.66, that's the rotational losses. So the sum of those two gives you the electromechanical power developed by the motor. So that's 104, 15.68 plus 516.66. That's 10,932.34 watt. That's the electromechanical power. So the process is fairly the same as before. So here we need to figure out IA and EB. So then if we compare it with the previous calculation, we can write this as EB times IA is equal to 10,932.34. This is the first equation. And then the voltage loop here, that equation is VA equals EB plus IARA. That's the 495 equals EB plus resistance 2.23 times IA. That's the second equation. And everything else is the same except this value here. So then if we substitute that, multiply this by EB, we have EB squared plus 2.23 IA EB minus 495 EB equals 0. And then this term turns out to be this value here. So EB squared minus 495 EB plus this value multiplied by 2.23, which is 24379.1. So compared with the previous one, only this term changes. Other bits are the same, only this part changes. Then again, if we apply this the solution, you'll have EB equals 495 plus or minus 495 24379.1 by 2. So you have 495 plus or minus 384 or 6 divided by 2. So we already know it's the positive term that's the valid one. So positive result, we'll just take the positive result. That will be 439.53 volts, and the corresponding current IA will be this value divided by this voltage, 10,932.34 divided by that gives you 24.87 amperes. So just this equation. So we have EB and then this divided by EB, this value. Yeah, get the current to achieve that PEM. Yeah. So next, so then you have to figure out the field current as well. So the calculation is the same. We have like the first rated condition, EB1, EB2 is equal to IF1 speed 1 divided by IF2 speed 2. This is the new condition. So IF2 will be IF1, IF2, sorry, 2 times EB2, EB1, and IF1 was from the previous question. So rated conditions, this is 2.18 and this is 1,500 over 2,500 times the back EMF we want is 439.53 and the rated back EMF is 428.4. So this will be the new field current. So that will be 1.336 amperes field current. So the last part is the DC machine operation as a generator. So the circuit remains the same, but the calculations, there's a slight difference in how you calculate everything. So now part 1 says the DC motor is now connected to a turbine rotating at rated speed. If the field circuit is supplied at its rated voltage, calculate the generated open circuit voltage. So now if we redraw the same circuit, so now this is working as a generator, so this is being driven by a turbine, let's say some prime mover. So this drives the machine at 1,500 RPM. The field circuit is at its rated conditions. So we need to figure out the open circuit voltage. So if this terminal, the armature terminal is open circuited, so that means the current out of the generator, IA, is 0. So this voltage, EB, the voltage drop here is 0 because there's no current. So the terminal voltage will equal the back EMF since there's no voltage drop in this case. So this EB is proportional to field current times speed. So that's, if we can figure that out from the rated conditions. So at rated conditions, EB was 428.4 volts. So the back EMF remains the same if the speed is the same and the field current is the same. So that's the value, and the terminal voltage will be the same as well. VA EB times IARA. Sorry, this is the current. So the voltage drop is this way. So here it will be minus IARA, and this term here is 0 because it's not conducting any current. EB, and that will be 428.4 volts as well. This is for first part. Um, so second part is it says the generator is loaded until the armature current is at its rated value. Calculate the terminal voltage and output power delivered at this operating condition. So that means now you are connecting some load here. So now the armature current rises to the rated value, which is 29.9. So part B, second part of that, now the armature current is at its rated value 29.9 amperes. So now it's the current is out of the machine, so it's working as a generator. The voltage drop here is this way. So now we can apply VA equals EB minus IARA condition. So mind this one is not plus here. For a generator, the current is going out of the machine, so this is a voltage drop that gets subtracted from the back EMF, so it's minus there. So here EB is 428.4 minus rated current 29.9, and the armature resistance is 2.23. So this is the voltage you'll have at the terminal of the armature. Which is 361.7 volts. So although this is delivering the rated current, the power output will be less. So the output power P out, so mind that for a generator, P out represents the power coming out of this armature terminal. It's a source now. As if you look at it as a system, the output power output is from, that's the electrical power output. So that this will be just VA times IA, which is 361.7 times 29.9. The voltage, armature voltage times the current gives you 10,815.5 watt output power. So if you look at this, this is below the rated output power condition. Let's say if you want more power, then you'll have to speed up the turbine more to get more power out of this. So let's say if you want to increase the voltage to rated value, then you'll need a higher voltage here. So you need to increase the speed. So the third part of that says the generator speed is increased and it's electrically loaded such that the terminal voltage and current are at its rated values. The field voltage is unchanged. Calculate the new back EMF and turbine speed required to achieve this operating condition. So I'll draw, let's say, another circuit for that condition. So now it's at a different speed. So this is electrically loaded such that now the voltage here is 495 and it's feeding a current of 29.9, and this is being driven at a certain speed to achieve this operating condition. So then we can find the back EMF required to achieve this condition, let's say EB new. So you have a voltage drop here. So this voltage plus the voltage drop gives you the new back EMF. So EB new will be, this is 2.23 ohm. This is the current voltage. So 495 plus the voltage drop across the resistance, which is 2.23 times 29.9. So this gives you the required back EMF, which is 561.67 volts. That's the back EMF you want. So to achieve this, you need to speed it up more. So the speed is proportional to back EMF. So if the field winding is constant, the new speed. So we have 1,500 RPM when it's running at 428.4, and then we want to find the speed when it's running, when it's producing 561.67 volts. So this is the speed it has to run at to achieve that voltage, which is 1966.6 RPM. Any questions on that? So fourth part of that, calculate the efficiency for the above operating condition in 3. So now it's working as a generator. So this is the output power. So 495 times 29.9. That's the output power, and the input power includes the power you put in from this shaft. So we can write, this is the shaft power, and then in addition to that you also have a field winding. So let's say some field circuit here which has the rated field 300 volts and current of 2.18, and this consumes some amount of power as well. So here we can find the output power will be this voltage times current. So that's 495 times 29.9. That's so 14.805 kilowatt. So it's producing this much of power. The input power includes the output power plus the copper losses in the armature. So copper losses in the armature plus the copper losses in the field winding plus the rotational losses. This is the total power input into the system. This bit here is the total power input from the turbine, and this part is from the field winding. That's the total power input into the whole system. So this we know, that's this one, copper armature copper losses. That's I squared R, so we can write that as 29.9 squared times 2.23. Which is 1993.6 watt, and the field winding copper losses, that's VFIF which we calculated before as well. That's 300 times 2.18 is 654 watt. And the rotational losses, we assume it scales linearly with speed. So P rotational losses at this particular speed of 1966.6. So we have 310 watt rotational loss, that this is at 1500 RPM, and then we scale it up to 1966.6. which is 406.4 watt. So if you add everything up together, you'll get the total input power. So P in will be 406.4 plus 654 plus 1993.6. Gives you, so this whole lot is 3.054 kilowatt, and that plus 14.85 gives you 17.8545. So output power is 14.8005. Input power is 17.8545. As percentage gives you efficiency. So that's 82.9% efficiency for this operation as a generator. So this bit I drew here is the power input from the shaft, this part here. This part is the P shaft power. That's input power from the turbine. And you add it up with the copper losses as well. That's the total input power to the system. All the power input, and you get out 14.805 kilowatts. So the last part says the turbine is speed is fixed at the speed calculated in the above case. The no loads voltage is required to be maintained at rated voltage. Calculate the field weakening operating condition, i.e. the field weakening current required to maintain this condition. So if this is working as a generator, let's say you can't control the turbine speed fast enough to control the voltage you want. So let's say you suddenly switch off a voltage and you don't want the voltage, terminal voltage, to rise up suddenly. So it has to have some control. So the only option is to reduce the field current. So that's pretty much what they do in synchronous, like alternators and stuff, car alternators and synchronous generators. You control the field current to reduce the terminal voltage. So here we now remove the load. So the last part.